Hello and welcome. This is the second video in chapter 27, and in this video we're going to be talking about how we actually visualize what's happening to the electrons in a wire as they're going through this metal. And so we have to again remind ourselves of what the model of a conductor is. A conductor is a positively charged grid, or a grid of positively charged atoms, and then an ideal gas of freely moving electrons. The electrons are too small. I mean, an ideal gas, the ideal gas is molecules, they collide with each other. The electrons are too small to collide with each other, but they're usually colliding with the atoms, the positively charged atoms. And don't think that they collide and stick with them. They have enough energy to where they just bounce off. And another important picture to consider about this is that the positively charged ions are vibrating, right? So this dynamic picture is that you've got these ions that are vibrating kind of at a random rate according to the overall temperature of the metal. And that will become important when we analyze what's going on in the context of resistance. So when we apply an electric field, what happens? When we apply an electric field, then these electrons that are just randomly moving around, they're going to still have that random motion, but now it's going to be kind of pulled towards the direction, I guess, against the field actually, because they're negative charge. So in the direction of the applied field, the electrons are going to feel a force opposite that of the field. So they're going to start to drift in the opposite direction. And so a good analogy to think of is if you take a big pegboard, like a board with lots of different pegs on it, and you just kind of drop a ball through it, the balls kind of bounce off of the pegs while it falls towards the ground. This is the same analogy to keep in mind of what the electrons are doing. The electrons are they're being accelerated by the electric field, and then they bounce into the atoms. And then they're accelerated by the field, and they bounce into the atoms, bounce into the atoms, and bounce into the atoms. So the atoms are constantly being bombarded by these electrons. And thinking again about how these atoms are vibrating randomly, these collisions that the electrons have with the atoms make the atoms vibrate more. They give the atoms more energy. And that in turn raises the overall temperature of the solid, because as you remember from thermodynamics, the temperature of a metal is proportional to the average energy per molecule in the metal. And so the collisions cause these atoms to vibrate more violently, and so that effectively increases the target of the electrons to bump into them. So they bump into them more, and it gets kind of clogged. And so there's actually less current with increased temperature. But going back to this increase in speed, this is kind of a picture to keep in mind when you think of like dropping a ball and watching it bounce as it comes to rest, right? The speed increases, then it bounces, then speed increases, then it bounces, speed increases, then it bounces. This is the same thing that's happening to the electrons in the electric field. And the drift velocity here can be expressed as an average acceleration over kind of an average time interval. Actually, it's a constant acceleration over an average time interval. And so the acceleration is, well, it's still force over mass, which is little e times big E over mass of the electrons. That m is mass of the electrons. And tau is what's called the average time between collisions. This is about the average time in between bumping in from one atom to the next. And that tau will be heavily temperature dependent, as we might see in a later example. So this is where you can start to make small changes to the electron current. If you remember, electron current was number density times area times drift velocity. So now we see that the electron current depends on the applied electric field. This is the change that we can make. And so the electron current depends on the charge and mass of the electron. It depends on the size of the wire. A, it depends on the metal in particular, N sub B, but it also depends on the electric field that's applied. An electric field that's applied, that's dependent upon the experimenter deciding on an electric field. And so the previous discussion about electron current is kind of a motivator for the idea of conventional current. Conventional current is what we all measure in the ammeters and in the circuits labs and on our electronic devices. This is the actual value of current that's measured. And it's similar to electron current, but it has one big difference. It is measured or defined as the amount of positive charge that passes through a cross-sectional area, positive charge, not total electrons, in a certain unit of time. And this bottom equation here shows how the conventional current is related to the electron current. Because if conventional current is equal to total charge over total time, well, we know total charge is always an integer number times the electric charge of the electron. And so then we just add this extra factor of the electron charge to the electron current. One side note is that this is actually how the Coulomb is defined. The Coulomb, by the way, the units of current are coulombs per second or amps, but the Coulomb is technically defined as an amp second. That is, a Coulomb is the amount of charge that passes through a wire with 1 amp of current in 1 second. That's technically how we define the Coulomb in the SI unit. So charge has the units of current times time, and that actually is a common unit in smartphone, tablet, laptop batteries. Those batteries have a certain amount of charge that is stored on them, and that unit is current times time. Typically, it's milliamps for the unit of current and hours for the for the time. So you can convert that to coulombs if you want. It's not a big deal. Basically, it's just like multiplying by a factor of 3. Because the current in your devices is usually a total of milliamps, and it's usually running for a number of hours, and so it just makes the unit realistic, because no one's going to think of how much laptop or how much charge their iPhone battery holds in terms of coulombs. It's just in terms of the useful thing, milliamps in a certain number of hours. Obviously, we have to be aware of the sign convention. Current is not a vector. It is a scalar, but the direction of conventional current is actually opposite that of negative charge massive flow. So if the electrons are moving to the left, that means physical mass is moving to the left. There's physical momentum in that direction. Actually, in this picture, we would have electrons mass actually moving to the right. That's going to make positive charge move to the left. So just because mass isn't moving to the left doesn't mean charge can be moving to the left. Charge is different from mass. And continuing with that, in a wire, sometimes it's useful to express the current in terms of a current density. So a current density kind of breaks up the cross-sectional area of the wire into small little sections, and the current density would be the amount of current in that specific section. Right, so keep the numbers simple. If you have a current of 1 amp and you take the cross-sectional wire, break it up into 10 little pieces, then the current density would be 0.1 amps per each one of those little pieces. Because when you add up the area of the 10 pieces, you get the total current. So it turns out to be an interesting quantity. It's going to show up in chapter 29 when we get to magnetism, but it's defined as the total current over the total area if the current density is constant. If the current density is not constant, you have to integrate that current density over the entirety of the cross-sectional area and get a resulting integration. That integration is what is going to be the current. So definitely that reinforces the idea that current is a scalar because it's a result of an integral. A lot of times people think that when current passes through one light bulb, it gets used up. What happens is that current isn't being used up, it's energy. So energy is the thing that's being used up in both these light bulbs as the capacitor gets discharged. And the idea of conservation of current, the fact that current has to be the same everywhere along a wire, that's just because if it wasn't, then charge would pile up somewhere. And then if charge piles up somewhere, then eventually it's going to repel the current, that the charge that's coming into that spot, and it's pushing away current or charge that's leaving that spot. So you would get kind of like a pileup on the highway, right? On a highway, when you have current or when you have cars flowing on the streets, right? That's, if there's an accident, then there's 0 cars going after the accident and everything's backed up behind the accident. That's the same thing here, but that never happens. You never observe that happening. So we kind of logically deduce that current has to be conserved because if it wasn't conserved, then we wouldn't have current. And we never observe that. So current has to be conserved in a wire. But that means that, going back to this equation, if the current I has to be constant, that means current density can change. If you have a big wire and then you solder it to a small wire, what you'll see is that the current density increases. This is like squeezing water through a tiny nozzle, or by putting your thumb on a garden hose. This is the same flow rate analogy as that, because when you put your thumb on the nozzle, the flow rate has to be the same. In this case, it's the current that has to be the same. So decreasing the area would increase the velocity. Same thing here. Decreasing the area would have to increase the current density. You're squeezing more electrons through that tube. And this is actually even more important, and it's a consequence of the conservation of current, the so-called junction rule. So that means if current is conserved, just like a laminar fluid, non-viscous fluid flow in pipes, if the current going in has to equal the current going out, and that's going to be very useful when we do electric circuits in chapter 28. And so putting this all together, if we go back to the equations relating current density to area, if we go back to this equation here, we knew that current was equal to E times electron current, but that had everything divided by with an A, so the A cancels, and we're left with what's called a macroscopic Ohm's law, where J, the current density, equals sigma times the electric field, and that sigma is this concept. It's the concept of conductivity. You see, the conductivity is a bunch of parameters that depend only on the material, and we have this what's called a microscopic microscopic Ohm's law. Current density equals conductivity times the electric field. So that means that inside the wire, the electric field at every location inside that wire induces a current density at that location. By adding up all the current density vectors gives you the current. So that's a microscopic version of Ohm's law. So in the final video of this section, we will discuss how we go from the microscopic version of Ohm's law to the macroscopic version of Ohm's law, which is might be the familiar equation relating the conventional current through a wire related to the voltage that's applied across it. So that's it for this video. As usual, thanks for your time, and we'll see you back here for the third and final video of chapter 27. Thanks for your time. Take care.